June 4th, 1942. 22 a.m., 4 miles above the Pacific Ocean, Lieutenant Commander Wade McCluskey stared down at 4 Japanese aircraft carriers turning lazy circles in the water. His fuel gauge showed 8 minutes of flight time remaining. In 7 minutes, those carriers would launch 200 fighters and bombers that would finish off what remained of the American fleet at Midway. McCluskey pushed his Douglas SBD Dauntless into a 70-degree dive. The plane that wasn't supposed to work was about to change the war. Before we continue with McCluskey's incredible story, we need your help to keep these forgotten heroes alive. If you're already hooked by what you're hearing, hit that like button right now. It tells YouTube to share this with more people who care about real history. Subscribe to this channel so you never miss another story of courage and innovation from World War II. And here's something we love. Drop a comment below and tell us where you're watching from, your country, your city. We have viewers from Buenos Aires to Berlin, from Manila to Montreal. Are you a veteran? Did your grandfather serve? Do you have a connection to this war? We want to hear from you. Now back to June 4th, 1942, where McCluskey was about to test everything a quiet engineer from Los Angeles had promised 3 years earlier. Ed Heinemann was 29 years old when the Navy told him to design an impossible airplane. He'd never graduated from college. He'd started as a draftsman at Douglas Aircraft, making $18 a week, drawing propeller blades and landing gear struts. He had a habit of staying late at the factory in El Segundo, walking between the half-built planes with a notepad, measuring things other engineers never thought to measure. The Navy's requirements in 1938 seemed simple on paper. Build a scout bomber that could operate from aircraft carriers, carry a 1,000-pound bomb, dive at terminal velocity without disintegrating, pull out of that dive without killing the pilot, and do it all while weighing less than the previous model. Oh, and make it fast enough to outrun Japanese fighters, and give it enough range to search 200 miles of empty ocean and still make it home. Every other aircraft company in America told the Navy it couldn't be done. The mathematics didn't work. A plane strong enough to survive combat dives would be too heavy to take off from a carrier deck. A plane light enough for carrier operations would tear apart at 240 knots in a dive. You could have one or the other, not both. Heinemann didn't say it was impossible. He said it would take 6 months. He'd grown up in Los Angeles watching his father repair motorcycles. His father had taught him something most engineers never learned. Every part on a machine is either doing something essential or it's dead weight, making everything else work harder. Find the dead weight, remove it, and suddenly the impossible becomes simple. Heinemann started with a radical idea that made senior engineers at Douglas uncomfortable. What if they stopped adding strength and started removing weight? The problem with dive bombers in 1938 was that everyone designed them like fighters that happened to carry bombs, heavy armor, multiple guns, complicated hydraulic systems, retractable tail wheels. All of it added pounds, and pounds meant you needed bigger engines, which meant more fuel, which meant more weight, which meant weaker performance. Between January 1937 and August 1938, the Navy lost 43 dive bombers. 43 planes, 86 pilots and radio operators, all of them flying the Northrop BT-1, the plane Heinemann's design was supposed to replace. They died the same way, every time. The BT-1 would enter a dive at 10,000 feet, accelerate past 250 knots, and the tail would flutter, a vibration that started small but grew exponentially. Pilots called it the shimmy. At 260 knots, the shimmy became a violent oscillation. At 270 knots, the tail control surfaces would tear off. The plane would tumble, inverted, straight into the ocean at 300 miles per hour. Nobody walked away from the shimmy. Lieutenant Robert Chen from Sacramento was the first pilot Heinemann personally knew who died this way. Chen had visited the Douglas factory 3 weeks before his crash, asking Heinemann technical questions about dive angles and stress loads. Chen had a wife pregnant with their first child. He told Heinemann he was nervous about the BT-1's high-speed handling, that something felt wrong during recovery pulls. "Just feels loose, you know," Chen had said. "Like the tail wants to go somewhere the nose isn't going." Chen died on August 12, 1938, during a training exercise off San Diego. Witnesses said his BT-1 entered a routine 45-degree dive, then seemed to snap sideways at 3. It drew 0 feet. The tail section was found 200 yards from the main wreckage. Heinemann attended the funeral. Chen's wife was 7 months pregnant. She asked Heinemann if her husband had been a good pilot, if he'd done something wrong. Heinemann told her the truth. Her husband was an excellent pilot. The plane had failed him. He drove back to El Segundo that night and didn't leave the factory for 3 days. The Navy's investigation blamed pilot error and excessive dive angle. Heinemann knew that was bureaucratic cover. He'd done the mathematics. He'd calculated the stress loads. The BT-1's tail was exactly strong enough for normal flight and exactly too weak for combat dives. It existed in an engineering failure zone where it would pass all the ground tests and kill people in the air. 3 more pilots died in September, 5 in October, 2 in November. The pattern was obvious to anyone willing to look at the crash reports. Every single pilot died during the pullout from a dive, when the plane was experiencing maximum G-forces and maximum airspeed. The moment when you needed the tail to be strongest, it was at its weakest point. Heinemann pulled the structural drawings for the BT-1 and started cutting. His insight was brutally simple. The tail didn't need to be reinforced. It needed to be completely redesigned with a different load path. Instead of trying to make a weak structure stronger with more material, he would create a structure that was fundamentally stronger with less material. The BT-1's tail used an internal framework of lightweight aluminum ribs covered by fabric. Industry standard. Same design every aircraft manufacturer used. The fabric kept the weight down, and the internal framework provided shape. The problem was that fabric flexed. At 250 knots, that flex became a harmonic oscillation. The faster you went, the worse it got, until the internal framework couldn't handle the vibration loads and ripped itself apart from the inside. Heinemann's solution seemed reckless. Replace the fabric with perforated metal plates. Make the entire tail out of aluminum, but drill thousands of small holes in the skin to keep the weight manageable. The holes would reduce weight by 38% compared to solid metal, while the metal skin would eliminate the flex that caused the harmonic oscillation. His supervisor told him it wouldn't work. Perforated metal would create drag. It would compromise the structural integrity. It was an untested design that violated standard aeronautical engineering principles. Heinemann built it anyway. He had access to a small wind tunnel at the Douglas facility in Santa Monica. At night, after the day shift went home, he would drive to Santa Monica with tail section mock-ups and run them through airflow tests. He tested 17 different hole patterns over 4 weeks. Circular holes, oval holes, diamond patterns, hexagonal patterns. The breakthrough came at 2:40 a.m. on a Tuesday in November 1938. Hexagonal holes, 0, 6 inches across, spaced at 1, 2-inch intervals, arranged in a honeycomb pattern. At 280 knots of simulated airflow, the perforated metal tail showed 0 harmonic oscillation, 0 flutter. The airflow passed through the holes with minimal turbulence, and the metal skin was rigid enough to maintain its shape under maximum stress. Heinemann ran the test 11 more times to be certain, same result every time. He took the data to Douglas's chief engineer at 7:00 a.m. that morning. The chief engineer looked at the wind tunnel reports, looked at Heinemann, and asked how much the new tail would weigh compared to the old one. 47 pounds less, Heinemann said. Build it, the chief engineer said. But Heinemann wasn't done. He'd solved the tail problem, but the plane was still too heavy. The BT-1 weighed 100 pounds fully loaded, and that was with a relatively weak engine. If he wanted the new dive bomber to outperform Japanese fighters, he needed to cut at least 600 pounds from the airframe. He started removing everything that wasn't essential. The retractable tail wheel? Gone. Replace it with a fixed tail wheel in a streamlined fairing. Saved 42 pounds. The complicated hydraulic system for the wing flaps? Gone. Replace it with a simpler mechanical system. Saved 87 pounds. The armor plating behind the pilot's seat? Keep it. That was essential, but move it forward 3 inches so it also protected the fuel tank. Eliminated the need for separate fuel tank armor. Saved 61 pounds. The internal bomb bay. This was the controversial one. Every dive bomber in the world carried its bombs inside the fuselage to reduce drag. Heinemann looked at the numbers and realized the internal bomb bay added 220 pounds of structural support that only mattered during the 30 seconds between releasing the bomb and pulling out of the dive. He moved the bomb to an external mounting rack under the fuselage. His supervisor nearly fired him. An external bomb would create enormous drag. It would reduce the plane's top speed by at least 30 miles per hour. It would make the plane vulnerable during the approach. Heinemann showed him something nobody had thought about. With an external bomb rack, you could add a displacement gear that would swing the bomb forward and down when released, ensuring it dropped cleanly away from the propeller arc during a vertical dive. With an internal bomb bay, you had to pull out of the dive before releasing or risk the bomb hitting your own propeller. The external rack actually made the plane safer during the most dangerous part of the attack, and it saved 220 pounds. By March 1939, Heinemann had cut 640 pounds from the BT-1's design. He'd redesigned the tail, simplified the hydraulics, repositioned the armor, moved the bomb external, and made 73 other small changes that each saved a few pounds here and there. He called it the XBT-2. The Navy would rename it the SBD, Scout Bomber Douglas. The prototype flew for the first time on April 25, 1939. Test pilot John Cable took it up to 12 feet over the Pacific and put it into a 60-degree dive. He later reported that the controls felt solid as a brick house all the way down to 300 knots. Zero flutter. Zero oscillation. The perforated tail performed exactly as Heinemann had calculated. Cable pulled out of the dive at 500 feet with enough control authority to execute a barrel roll just to prove the point. The Navy ordered 57 production models in October 1939. They ordered 144 more in February 1940. By December 1940, they'd ordered 584. By the time Japanese planes appeared over Pearl Harbor on December 7, 1941, the Navy had taken delivery of 246 SBD Dauntlesses. But here's what the Navy didn't understand. Heinemann hadn't just designed a plane. He'd designed a weapons system that would only reveal its true purpose under combat conditions nobody had predicted. The SBD's perforated tail wasn't just stable at high speed. It was stable during the exact maneuver that would define the Pacific War, the near-vertical dive-bombing attack on moving ships. To understand why this mattered, you need to understand how dive bombing was supposed to work in 1941. Standard doctrine called for a 45-degree dive from 10 feet, bomb release at 3 feet, pull out at 500 feet. This gave the pilot time to aim, time to adjust for wind and ship movement, and time to escape. The problem was that a 45-degree dive gave ship gunners 17 seconds of tracking time. 17 seconds to calculate your flight path and fill the air with anti-aircraft fire. Japanese ships in 1942 carried between 16 and 40 anti-aircraft guns each. 17 seconds was an eternity. The first Navy pilots who tried to take SBDs into combat at the Battle of Coral Sea in May 1942 discovered something Heinemann's design had made possible. If you pushed the dive angle to 70 degrees, the ship gunners had less than 8 seconds of tracking time. The steep angle also meant you were coming straight down at the target, which made you a much harder target to lead. But a 70-degree dive meant you were pulling more than 5 Gs during the recovery. That level of stress would have disintegrated a BT-1. The SBD's perforated tail just absorbed it. Lieutenant Commander Bob Dixon led a squadron of SBDs during the Battle of Coral Sea. He watched 3 of his pilots push their dives past 65 degrees and put their bombs directly through the flight deck of the Japanese carrier Shoho. One pilot, Ensign John Lepler from Wichita, entered his dive at such a steep angle that witnesses thought he'd been hit and was crashing. Lepler pulled out 50 feet above the water with his bomb inside Shoho's forward elevator shaft. Dixon reported back to Fleet Command that the SBD could handle dive angles nobody had thought possible. His exact words, "This plane is stronger than we are." That information reached every carrier in the Pacific Fleet within 48 hours. At Midway, 3 weeks later, that information saved the American fleet. Wade McCluskey's SBDs had been searching for the Japanese carriers for over 2 hours. They'd flown their search pattern. They'd found nothing. They were 7 minutes from bingo fuel, the point where they wouldn't have enough fuel to return to the USS Enterprise. McCluskey made a decision that violated Navy doctrine. He kept searching. At 10:20 a.m., he spotted a Japanese destroyer traveling at high speed. He followed its wake and found 4 Japanese carriers, Akagi, Kaga, Soryu, and Hiryu. All 4 were refueling and rearming planes on their flight decks. Their fighters were at low altitude, chasing American torpedo bombers. The carriers were completely exposed. McCluskey had 37 SBDs. The Japanese had 96 fighters and 248 anti-aircraft guns protecting those carriers. Standard doctrine said you couldn't attack without fighter escort. Standard doctrine said you needed to coordinate with torpedo bombers to divide the enemy's defensive fire. Standard doctrine said a lot of things. McCluskey looked at those 4 carriers and thought about what Dixon had reported from Coral Sea. This plane is stronger than we are. He pushed his SBD vertical and dove straight at Akagi from 14,000 feet. The dive angle was 78 degrees, nearly straight down. The airspeed indicator hit 276 knots. The perforated tail sang with the airflow, a high-pitched whistle his radio man could hear over the engine. The Japanese gunners never got a tracking solution. McCluskey was moving too fast, at too steep an angle. He released his 1,000-pound bomb at 1,800 feet, direct hit on Akagi's flight deck. The bomb penetrated through to the hangar bay where 18 fueled and armed planes were waiting. The explosion set off a chain reaction that gutted the carrier. 36 more SBDs followed him down. In 6 minutes, American dive bombers destroyed 3 Japanese aircraft carriers, Akagi, Kaga, and Soryu. All 3 were sunk by bombs that hit during near-vertical dives that shouldn't have been survivable for the attacking planes. Hiryu, the 4th carrier, was hit 4 hours later. Same tactic, 70-degree dives. The Japanese air officer on Hiryu's bridge reportedly watched the SBDs coming down and told his captain, "Those planes should be ripping themselves apart. Why are they not ripping themselves apart?" The answer was 640 pounds of weight that Ed Heinemann had removed, and a perforated tail that had been wind tunnel tested at 2:40 a.m. on a Tuesday night when nobody was watching. The Battle of Midway turned the Pacific War. 4 Japanese carriers lost. The SBD Dauntless was credited with sinking all 4. Word spread fast. By July 1942, every SBD pilot in the Pacific knew they could push their dives steeper than doctrine allowed. By August, the standard attack profile was 70 degrees. By October, some pilots were exceeding 80 degrees. The mathematics was simple. A steeper dive meant less time in the enemy's engagement envelope, which meant higher survival rates. Between May and December 1942, SBDs flew 4 823 combat sorties. 142 planes were shot down. That was a loss rate of 2. 9%. By comparison, the old BT-1 had a training loss rate of 1%. The SBD was safer in combat than its predecessor had been during peacetime training, the Japanese noticed. Intercepted radio traffic from Japanese fighter pilots in late 1942 showed increasing frustration with the American dive bombers. One pilot reported, "These planes dive too fast. Cannot establish tracking angle. When I try to follow, my plane approaches structural limits. American pilot pulls out. I must break off." The Japanese had excellent fighters. The Zero could outturn, outclimb, and outmaneuver the SBD in every metric except one. The Zero's lightweight structure meant it couldn't safely exceed 240 knots in a dive without risking structural failure. The SBD could hit 280 knots and pull out without stress. Japanese fighters learned to avoid pursuing SBDs into vertical dives. It was a losing proposition. By mid-1943, the SBD had sunk more Japanese shipping than any other Allied aircraft. 6 carriers, 14 cruisers, 6 destroyers, countless cargo vessels and support ships. The official Navy tally in December 1943 estimated the SBD had sunk or damaged ships totaling 290,000 tons of displacement, and Ed Heinemann received almost no recognition. The Navy's official reports credited the skill and courage of American pilots for the victories at Coral Sea and Midway. Douglas Aircraft's publicity department ran advertisements celebrating America's premier dive bomber without mentioning who designed it. Aviation magazines published detailed analyses of the SBD's combat performance and speculated about what engineering innovations made it so effective, but Heinemann's name appeared nowhere. He was fine with that. He was already working on the next project. In December 1942, the Navy came to Douglas with a new requirement: design a dive bomber that could fly from the new Midway-class carriers and carry a 2,000-pound bomb. Heinemann started cutting weight again. The war ended before that plane entered production, but the design became the foundation for the A-4 Skyhawk, which would serve the Navy for 43 years. Heinemann spent the rest of his career at Douglas, eventually becoming Vice President of Engineering. He designed the A-3 Sky Warrior, the A-4 Skyhawk, and the F-3D Sky Knight. Every one of them followed the same principle: cut the weight, keep only what's essential, and make the structure fundamentally stronger rather than just heavier. He won the Collier Trophy in 1953. He was inducted into the National Aviation Hall of Fame in 1981. But most people who knew his name knew him as the father of the Skyhawk, not as the man who designed the plane that won Midway. Heinemann retired in 1962 and moved to Palos Verdes, California. He spent his retirement sailing and reading engineering textbooks. He didn't talk much about the war. When people asked him about the SBD, he'd usually say something like, "Good plane, simple design, did what it was supposed to do." He never mentioned the wind tunnel tests at 2:40 a.m. He never mentioned the 640 pounds. He never mentioned Lieutenant Robert Chen, whose death had started everything. Ed Heinemann died on November 26, 1991, at the age of 83. His obituary in the Los Angeles Times mentioned his work on the Skyhawk and his Collier Trophy. It didn't mention the SBD Dauntless. It didn't mention Midway. There's a small display at the Palm Springs Air Museum dedicated to the SBD Dauntless. It includes a cutaway section showing the perforated tail structure. The placard explains that the perforation pattern reduced weight while maintaining strength, and notes that this innovation was typical of wartime engineering efficiency. It doesn't mention Heinemann's name, but if you talk to the surviving SBD pilots, and there aren't many left now, they'll tell you about the plane that could dive steeper than physics said it should, pull out harder than the manual said it could, and bring them home when every other plane would have come apart. They'll tell you it was the most honest airplane ever built. No tricks, no compromises, Just a fundamentally good design that did exactly what it was built to do, every single time. Lieutenant Commander Wade McCluskey, who led the dive that destroyed Akagi at Midway, flew SBDs for the rest of his combat tour. He survived the war and became a rear admiral. In a 1988 interview, at age 85, he was asked what he remembered most about the Battle of Midway. "The sound the plane made in that dive," McCluskey said. "The tail would sing, high-pitched whistle, like it was happy to be doing exactly what it was built for. I heard that sound and I knew I was going to make it home." That sound was air passing through 3 247 hexagonal perforations, each one exactly 0. 6 inches across, arranged in a honeycomb pattern that a 29-year-old engineer had tested in a wind tunnel in the middle of the night because he'd promised a widow that her husband hadn't died because of bad flying. Between 1940 and 1945, Douglas Aircraft built 5 936 SBD Dauntlesses. They flew in every major Pacific naval battle. They were credited with destroying 18 Japanese warships and 124 cargo vessels. They had the lowest loss rate of any American carrier aircraft during the war, and the man who designed them went back to his drafting table and started cutting weight from the next plane. If this story moved you, hit that like button. These forgotten engineers changed history with slide rules and wind tunnels and late nights in empty factories. They deserve to be remembered. Subscribe to this channel so you don't miss the next story. We've got dozens more about the people who won the war away from the battlefield. The designers, the mechanics, the innovators who made impossible things work. Drop a comment and tell us, did anyone in your family work in aircraft manufacturing during World War II? Did they have stories about the planes they built? We want to hear from you. Thank you for keeping these memories alive. The SBD Dauntless was officially retired from Navy service in 1959. By then, jet aircraft had made propeller-driven dive bombers obsolete. The last flight was performed at Naval Air Station Norfolk by a pilot who'd never heard of Ed Heinemann. He noticed the tail made a whistling sound during the dive. He mentioned it in his post-flight report. Nobody knew why it did that. Somewhere in Palos Verdes, Ed Heinemann was probably reading an engineering textbook and thinking about how to make the next plane lighter. The pilot who proved the math wrong, October 26, 1942, 11:47 a.m., Lieutenant Stanley Swede Vejtasa was alone at 18 to 0 feet above the Santa Cruz Islands with 5 Japanese Zero fighters climbing toward him. His SBD Dauntless had already dropped its bomb on the carrier Zuiho. He should have been heading back to the USS Enterprise. Instead, he was about to do something that would make engineers at Douglas Aircraft recalculate everything they thought they knew about their own airplane. Vejtasa was 26 years old, from Circle, Montana, population 487. He joined the Navy in 1937 because there were no jobs in Circle during the Depression. He'd washed out of fighter pilot training twice. His instructors said he was too aggressive and failed to follow established procedures. The Navy stuck him in dive bombers instead, figuring he could do less damage in a plane that was supposed to fly straight and drop bombs. They were wrong about that. What made Vejtasa different from every other SBD pilot in the Pacific Fleet was his background before the Navy. He'd spent 3 years as a stunt pilot at county fairs across Montana and Wyoming, flying a rebuilt Curtiss Jenny that had no business still being airborne. He'd learned to fly an aircraft that was structurally unsound, where every maneuver was a negotiation with physics and luck. He'd developed an instinct for knowing exactly how far you could push a plane before it pushed back. When he first flew the SBD in 1941, he'd told his squadron mates it was overbuilt. They'd laughed at him. Who complains about a plane being too strong? But Vejtasa meant something specific. The SBD had more structural strength than the Navy's flight manual acknowledged. He could feel it in the controls during recovery pulls. The plane wanted to do more than it was being asked to do. He'd been testing that theory in small ways for 8 months. Steeper dives than doctrine allowed, harder pullouts, tighter turns. The plane never complained. It never gave him the feedback that said, "Stop, you're approaching the limit." It just did what he asked. At Santa Cruz, with 5 Zeros climbing toward him, Veitasa was about to test his theory completely. Standard procedure when a dive bomber encountered enemy fighters was simple. Run. Dive away. Use your speed to create separation. Get low over the water, where the Zero's superior maneuverability didn't matter. Maybe fire your rear gun to keep them honest, but mostly just run. Veitasa looked at those 5 Zeros and thought about the math. The Zero could turn inside any American fighter. It could climb faster than anything the Navy had. But it was built light, so light that its airframe couldn't handle high G-turns at high speed. Japanese pilots had to be careful during aggressive maneuvers or risk structural failure. The SBD was built heavy. Heinemann had removed every pound he could, but what remained was solid. Overbuilt, like Veitasa said. What if, instead of running from fighters, you fought them using maneuvers they couldn't follow? Veitasa rolled, inverted, and pulled the SBD into a split S, a maneuver that dove the plane toward the ocean while reversing direction. The G-forces during the pullout were supposed to be dangerous for a dive bomber. The Navy manual said you could black out. It said you could overstress the airframe. Veitasa pulled 6 Gs. The plane shuddered but held. He came out of the split S at 300 knots, headed straight at the Zero formation. The Japanese pilots had to scatter. A dive bomber flying straight at you at 300 knots wasn't supposed to happen. It violated everything they knew about American tactics. Veitasa selected the closest Zero and opened fire with his forward guns, 2 50-caliber machine guns. Not much for air-to-air combat, but enough if you could hold your aim steady. He hit the Zero's engine. Smoke. The Japanese pilot broke left, trailing fire. The other 4 Zeros converged on Veitasa from 3 directions. He snap-rolled right, pulling the SBD through a barrel roll that should have been impossible for a plane that size and weight. 1 Zero overshot. Another couldn't match the roll rate and fell behind. Veitasa fired a 2-second burst at the Zero that overshot. Hits on the wing route. The Zero started losing altitude. His radio man, Bombardier First Class James Cales from Amarillo, Texas, was in the rear seat, trying to process what was happening. The Navy had trained him to operate the rear gun during defensive actions. He'd never trained for offensive dogfighting in a dive bomber. He started firing at anything that crossed his field of view. "Swede, what the hell are we doing?" Cales shouted over the intercom. "Winning," Veitasa said. 3 Zeros left. They'd regrouped and were coming at him in a coordinated attack. 1 high, 2 low. Standard fighter tactics. Box in the target, force him to commit to defending against one threat, then hit him from the other angle. Veitasa did something the Japanese pilots had never seen. He pulled the SBD vertical, a full vertical climb from 8,000 feet. The SBD wasn't a fighter. It didn't have the power-to-weight ratio for vertical climbs, except Veitasa had dropped his bomb, burned off half his fuel, and Heinemann had cut 640 pounds from the original design. The plane was light enough, and the engine had just enough power. He climbed 2,000 feet straight up, then kicked the rudder hard left and let the plane fall into a hammerhead stall, nose down, spinning on its vertical axis. The Zeros couldn't follow. They'd been climbing to intercept him at 8,000 feet. Suddenly, he was at 10,000 feet, inverted, falling back through their formation from above. He fired at the nearest Zero during the fall, hit the cockpit. The Zero rolled right and disappeared into a cloud deck, trailing debris. 2 Zeros left. They'd seen 3 of their squadron destroyed by a dive bomber. They broke off and headed back toward their carrier. Veitasa let them go. His fuel was low. He'd been in combat for 11 minutes, longer than any SBD pilot had survived, against multiple fighters. He turned back toward the Enterprise and checked his plane. No damage, no unusual vibrations, no warning indicators. The SBD was performing exactly as it had when he took off. When he landed on the Enterprise 23 minutes later, the deck crew counted 3 bullet holes in his tail section, close groupings, which meant he'd been in someone's sights. But the perforated tail had done its job. The bullets had passed through the honeycomb holes without hitting any structural members. Vetasa's after-action report was 5 pages long. He detailed every maneuver, every attack angle, every G-force load he'd pulled. He estimated he'd exceeded 6 Gs at least 4 times during the fight. He'd performed a snap roll at 280 knots. He'd climbed vertically for 2 Saruzeren feet. He concluded the report with one sentence. The SBD is capable of fighter-type maneuvers if pilot is willing to accept structural stress loads. The Navy's Aviation Command read the report and didn't believe it. They sent an investigator to interview Vetasa and his radioman separately. Kayleys confirmed every detail. The investigator checked the gun camera footage, grainy, hard to interpret, but it showed a 0 going down in flames after the SBD's forward guns fired. 3 confirmed Japanese fighters destroyed by a dive bomber in a turning dogfight. The Navy brass called Douglas Aircraft and asked a simple question: can your plane really do this? Douglas engineers pulled Vetasa's flight data and ran the numbers. The maneuvers he'd described, especially the vertical climb and the 6G pulls, should have exceeded the SBD's design limits. The plane should have experienced structural failure, except Ed Heinemann had never published the SBD's actual structural limits. He'd given the Navy the safe operating envelope, the range of maneuvers that any competent pilot could perform without risk. But the plane's true limits were higher, much higher. Heinemann had designed the SBD to survive the absolute worst-case scenario he could imagine: a full power dive to terminal velocity, followed by an emergency pull-out at maximum G-load, followed by an immediate second dive if the first attack failed. He'd calculated that as requiring a structural safety margin of 2 Gs. The Navy's flight manual listed the SBD's limit as 6 Gs. Heinemann had built in a 53% safety buffer and never told anyone. He figured pilots would push the envelope on their own, and he wanted them to survive when they did. Vetasa had accidentally discovered that buffer. Within 2 weeks, every SBD squadron in the Pacific received a classified technical bulletin. The SBD Dauntless possesses greater structural strength than previously documented. Pilots are advised that the aircraft can sustain maneuvers beyond published limits in emergency combat situations. The bulletin didn't explicitly authorize fighter-style dogfighting in a dive bomber, but it didn't forbid it either. Some pilots read that bulletin and kept flying the SBD exactly as they'd been trained. Others read it and started experimenting. By November 1942, there were at least 6 documented cases of SBD pilots engaging Japanese fighters in turning dogfights and surviving. One pilot, Lieutenant John Eldridge from Portland, Maine, reported shooting down a Zero after luring it into a high-speed dive. The Zero pilot had followed Eldridge down to 400 knots, expecting the American plane to disintegrate. Instead, Eldridge pulled out cleanly, and the Zero broke apart from the stress. "I didn't shoot him down," Eldridge wrote in his report. "His own plane did." The Japanese Naval Command noticed the pattern. Intelligence reports from late 1942 show increasing confusion about American dive bomber capabilities. One captured document from December 1942 included this note: "American bomber aircraft demonstrating fighter characteristics. Pilots advised to avoid extended engagements." By early 1943, the Zero's tactical advantage in the Pacific had diminished. Not because the Zero got worse, it was still an excellent fighter, but because American pilots had learned they could survive dogfights if they used their planes' hidden strengths. The SBD became something it was never intended to be. A multi-role aircraft that could bomb ships, fight fighters, and survive both missions. Veitasa flew 47 more combat missions in the SBD. He was credited with destroying 7 Japanese aircraft total, 3 at Santa Cruz, 4 more over the next 8 months. He survived the war, returned to Montana, and spent 33 years as a commercial pilot for Western Airlines. He never met Ed Heinemann. He didn't know that Heinemann had seen his Santa Cruz after-action report and kept a copy in his personal files. He didn't know that Heinemann used Veitasa's combat data to design even stronger tail structures for the next generation of Douglas aircraft. In 1985, at age 69, Veitasa was invited to speak at the Palm Springs Air Museum during an exhibition on Pacific War aviation. He stood in front of a restored SBD Dauntless and told the story about fighting 5 Zeros. Someone in the audience asked him if he'd been scared during the dogfight. "No," Veitasa said. "I was too busy trying things I'd always wanted to try but never had an excuse to. That plane wanted to fight. I just had to let it." Someone else asked if he'd known he was exceeding the plane's structural limits during the vertical climb. "I knew I was exceeding the published limits," Veitasa said. "But I could feel the plane telling me it had more to give. You fly enough hours in something, you learn to hear what it's saying." He paused and looked at the SBD on display behind him. "Whoever designed this plane," Veitasa said, "they understood something important. The plane shouldn't be the limiting factor. The pilot should be. Build the plane strong enough, and the pilot will figure out how to use that strength." Ed Heinemann had died 6 years earlier, but if he'd heard that, he probably would have smiled and gone back to his engineering textbook. Because that was exactly what he'd been trying to do since 2:40 a.m. on a Tuesday night in 1938, testing perforated metal in a wind tunnel while thinking about Lieutenant Robert Chen and all the pilots who died because their planes weren't strong enough. Build the plane strong enough, and the pilot will figure out the rest. That wasn't just engineering philosophy, that was how you won a war.